Okay, good morning. I'm going to talk about the future of programming will be live. So in the beginning, we have computers, we have binaries, electrons flying around, not very useful for getting work done. So we applied our, good friend abstraction to make the concrete bits into more abstract symbols that we can then manipulate and, write our programs. Right. So, and then, this evolves into programming languages. Very useful. Programming languages help us, they give us a language for our abstractions. They allow us to, you know, you know, record our abstract thinking and provide a limitation of that thinking and help us write programs. But where does the computer actually fall into the process of programming? So, we think really hard about our programs. The languages guide our thinking, but the computer is just kind of sitting around there doing nothing. It's not actually helping us think about our programs. It's not helping us write our programs. It's just sitting there and waiting for us to know what our programs are before we can type them in. Well, this isn't entirely true, of course. We have static type systems that give us errors that allow us to, tell us when our programs are bogus, or uh, code completion that allows us to sort of figure out what to type next, or even IDs that have debuggers. But I feel like we should be able to do more with that. And so live programming is this idea that you know today programming is like archery. We think about our programs, then we type them into the computer, and if it's wrong, then we go back, rethink, retype, and start the process over and over again. And then if you have a REPL, you can make that a little bit faster. But then if you have a large program, some programs don't work really well in REPLs, and it's just kind of like it's nice if you can have a little bit of a feedback loop while you're programming, but a lot of times you don't, right? And live programming, in contrast to archery, is like using a water hose to write your program, right? Water hose, you just sort of aim the water hose and you hit the target, bam. It's really easy. There's an Olympic sport for archery, and there doesn't need to be one for water hosing because water hosing is very easy. And this really is all about feedback loops, making the feedback more continuous, more integrated, more interactive, right? And the better feedback loops we can get while programming, the better programs. The faster we can write programs, the better programs we can write. So I've been working in this field of live programming since 2007, and I did this, this little language where you could type your code and you could see the output of your code while you were typing it. And I thought it was really cool at the time, but in retrospect, it wasn't that great because, as Brett Victor says, you can see sort of the typing, you can see the output, but you can make no connection between the two. So live programming has to be more than just running your program while it's, or editing your program while it's running. And I tried some other things, which I will talk about in just a second in a demo. But I think the overall experience is here. I try and keep failing, but hopefully we can do better. So let's get going with the first example, the first demos. And where is it? Oh, my taskbar is completely missing. That's not what I wanted. All right. So here we're going to have a textual environment. This is a little live program. Can you guys see that question mark okay? I hope so. The color is not very good on this projector. Right, so I type a question here, and it's basically a placeholder for a statement. I call it a holy term, right? It's like, it's a hole in your program, and then you can shape it into something else. So we can now do code completion on that, and we can draw a circle or draw a square, right? And what happens is that we get a little draw command here, and these holy terms are substituted with actual values in your program. So this is a geometry. There's even a color here, which is that color you see down there. And of course, the nice thing about this sort of holy term style of programming is that you every time you add something to your program, you have something that's executable, right? Even with default random values, but at least there's something there, so you get your feedback right away. So let's change that into a circle, right? So we did code completion again, and then we get other arguments here. This is a position, right? And the color's there. So let's add a position in here. It keeps jumping around, but that's just the way the random values work, right? So now we have a position with a tuple. We can do 100 by 100, right? Or I might want to do 200, right? But every time I edit this, right, you can see it's all jumping around and everything. So let's do this smoothly, right? We can just scrub to 200 if we want. This is called scrubbing, by the way. I'm using Brett Victor's terminology. It's basically the idea that you can have a value in a continuous domain and smoothly adjust it, right? And we can scrub this one too. We can also scrub both of them, right? But actually, that's kind of stupid. Let's just move it directly, right? I mean, that's really what you want to do, right? We can go to the color and we can change it to blue, but we can also scrub the color, right? So you just go around and choose a new color. It could be lime, or we can change this to a tuple, right? And we can do a little color picker here, right? So that's all well and done. Um, let's add another shape here. Let's add another rectangle. Now I can just tap on the screen and do it. Right. I'm adding a rectangle here. It's going to make it 30. Let's make this guy the same one too. Make that 60. Is that 30, 60, 60, 30? Okay. All right. So now we have two shapes here. And let's say we just want to align them together. Well, and to do that, you just define a variable, val x. We'll make it a wholly term. Then I'm going to drag x to 100. That becomes, now that swaps to 2, right? So now x equals 100, and then this other use of 100 becomes x, and I can do the same over here. Right now, when I move this, right, they're all bound together. This is how code works, right? We can do the same with the size. Holy. So now when I actually go and make this larger, right, you can see it's moving around. Okay, so this is okay. Maybe you might even think this is cool. There's some issues though, so let's go in and do a little bit more complicated example here. Now we have a ball here, circle, and then we're going to make this circle move. So on tick, that's just every tick, update it. We're going to say the position equals, oh wait, now I have to do other stuff here first. Do P, make that the position, make this the diameter, subtract. I want it to be a centered, it's okay. We just started that one. So maximize. Now you know it's real because it crashed, right? P, D, don't type 0. Divided by, is it 50? 2. Okay. So now we have a centered position, right? So I can move this like here, but if I change the size, right, you can see it changes from the center because position is expressed from the center. Right, and then we can go ahead and make the ball move. P equals P plus V divided by 50. Now we can see that the ball is moving, right? Of course, time is frozen at the 0 position, right? But we can go ahead and do that. Scrub the time, to see the thing. Right? We can also scrub the, wonderful. This didn't happen earlier in rehearsal, so. Anyways, you get the feeling, right? So all we're doing is we're making it move around, and yeah, I'm just going to move on here. But okay, but the one thing I want you to get out of this is that, okay, when I was doing all this other thing, changing the shape and changing the color, right? That was really easy, right? But that was really not what most of programming involves, right? And when I was actually making it move around, right, I wasn't actually using the live programming environment anymore. In fact, the live programming environment was crashing on me, was getting in the way. But even if it wasn't crashing, it would be distracting me, right? It's not good enough, right? We have to try harder. All right, so go back to the slides. Use Alt here, not that one. All right, slides, here we go. All right, so what's really cool about the demo I just showed you, it has a lot of the scrubbing behavior. If you think of your program as a continuous function, right? And think of your edits as sort of being small edits lead to small changes in the program's output, right? And that's what scrubbing supports, right? You can scrub up and down, your values. But it's not what we do in programming, right? In programming, we type in new abstractions, we type in things and make things appear, and we do a lot of discrete adjustments to our code, right? Things that can't be represented as a continuous function. But one of the things that really did work here was direct manipulation, so we should do more of that. So let's reset. We'll do another demo later that actually kind of explores, how we can do better. The one question we really need to ask here before we get into this work is, where do programs come from, right? Because programming languages is about these programming languages. They restrict your thoughts. They allow you to they provide the language for just talking about your abstractions, but the thinking all happens in your head. The computer does none of the thinking for you. It's stuck there. And I think this is why we've been stuck in text-based programming for so long, is that it is the ideal medium for that. It's efficient to interface with your mental model since everything is happening in your head. Text is the best way to sort of interface with that thinking, right? It's efficient for coding the results of your thoughts, and it's not distracting with feedback that might be off topic and wrong. Okay? But on the other hand, text is very abstract. It's not very concrete at all, and it doesn't allow it doesn't allow for much interaction outside your mind, right? You can't really manipulate text. When I was dragging those numbers down and making them the same, right, I was doing that in the most inefficient way possible. That's like the sort of the extent of how you can manipulate text. So why don't we think about visual programming again, right? This happens every 5 years or 10 years or so. Somebody will say, why don't we do visual programming? It can solve all these problems. But if you look at the way that we do visual programming, typically it's just textual programming with boxes, right? You have names on these abstractions, and it's still very abstract. And it's even worse if you have this abstract visual programming, right? You get this like literal spaghetti code, right? And you just see a bunch of lines and stuff, right? You haven't actually improved the situation a bit. So the goal for live programming is to capture and augment the thinking that goes on our heads. This is what I believe the goal is for this, right? Is to bring that thinking that's currently happening solely in your head, bring it out into the computer. And how are we going to do that? Well, let's go back to direct manipulation, right? Direct manipulation is this awesome way of sort of having, interfacing directly with a concrete system, right? Mac Paint is the first one that explored this in a UI paradigm. But we're also seeing a lot more interesting things now that we have holographic interfaces and stuff, right? And it really does allow you to sort of take it, but it's all concrete, right? Direct manipulation only works in the concrete world. To break out of that, right, we have programming by example, which was one of these research topics that was really hot in the 1990s. And basically, you write a bunch of examples and you let the computer magically abstract them into a program. Of course, computers aren't that smart, and they can only abstract simple examples, but it's nice in concept, right? Well, let's look for sort of a middle approach here, right? So how about live programming with examples? I mean, does everybody know what the magic wand does in Photoshop? Kind of, right? You put the wand down and it does an outline, it does edge detection for you, and it says, oh, there's a giraffe, right? I didn't actually have to draw that by myself, right? And that's what computers are really good at. They're really good at edge detection. So if we could just find our edges in our program, then the computers could say, oh, there's an edge here. Do you want to turn that into an abstraction? Maybe. So we can help abstract without requiring magic. So I'm going to do a few more demos here that go into that sort of line of thinking. Let's see if I can do this right. Escape. How do I? Okay, there we go. Let's do this one first. All right. So here we have a simple editor, simple line editor here. So I'm going to do a little bit of sort of geometric thought. So I'm going to draw a line. Right, there's a line, and you can see the code for the line appearing on the left. Right, if we draw another line here from this point, right, they share the same point. If we move this, right, we can see that they're stuck together. Now let's draw another line perpendicular to this one. And we don't have to draw it exactly perpendicular. The system will just infer that it's perpendicular enough. Now, if we look at the code, right, this is a perpendicular line. So if we change this, right, it moves, right? That's like, as a perpendicular line should. And then let's draw another line here to the intersection of where the perpendicular line hits that other line. So if I've done that well enough. Right, now you can see that this is an intersection, right? So I drew this and it automatically abstracted it into an intersection so that when I move this thing here, right, it stays in sync. You know, we can even move this down here and it will, you know, we'll just extrapolate the perpendicular line that's not down there, right? We can move everything, shoot. Everything gets smaller and harder to hit. Right, okay. So we've created this sort of nice program that allows us to, you know, do very specific, we didn't have to know about intersect or perp, those abstractions, but, you know, we just inferred it by the lines you drew, okay? So that's one way we can sort of boost this thinking. Let me show you another one. So let's go to, again, let's see if I can, I never understood Windows. All right, let's try this one. Right, so this is a Lexing example. So we're going to start with a string, and I'll say hello, curry on 2016, or I just do 16 at ecoop. Close. Right. So now we have a string. It's a concrete value. We're going to Lex this. So we're going to add a call here, and the first argument is going to be where that red thing is in the string. Okay, and we want this call to return true, so I'm going to just click on that. I have false and true and those kind of things. Right now this is true, and now I can click on this again, and I can get a set of methods that actually return true. So letter, digit, lower. Right now we do that. If we move this around here, you can say E is true, O is true, space is not a letter, so that's not true. This is all true, false, false. There we go. Right now we can open that up, do an if statement here. The if statement, the conditional of the if statement is just this true value that we just produced here. Now, when that's true, it opens up and we can write code in it. And when it's not true, it just closes. Let's see. Let me show you that really quick here. So that's false. Now it's closed. So when it's open, it's there. Right now, I can go ahead and do another call. And the argument will be the next character in that string, right? And now I don't want a truth value. I want another character, which is like the end of that, the character that I don't want to include in the token. And we just plop it right there. Now, if I move this around here, right, this is just you know, this is just a numeric offset, right? You'll see it just takes n levels, you know, it takes 1, 2, 3, 4, 5, 6 characters of the string, right? But of course, we can make that more general than 6 characters. We can abstract that, right? So I'm going to look at this, and it says, okay, letter star will also give you those 6 characters, but it will also give you more than that, because if I move this again, now, don't want cut. Right, you'll see it stays there, and then when it jumps to here, it goes to this, it goes over. Now I'm pointing at the screen. Can you guys all see this okay? Are those lines actually clear? They look washed out to me. All right, well, yeah, projectors are always troublesome here. Right, so now we're lexing the whole curry on thing, but we actually want this, actually want the 16 too, so we're going to go ahead and just remap this to here. So I thought I was going to remap it just to here. Come on, remap. There you go. Now the call reset because I want a different set of characters, right? And it gives us letter digit as the only possibility, right? So now it's going to give us letters and digits here, right? And it closes whenever it doesn't work. And then we can add space and we can add other things here too, just as easily as we did now. Okay, so that's cool, or I hope it's cool. Let's go do another example. let me hide this for now. So this is more of like a traditional diagram editor. So I'm going to draw a box here, right? And I'm going to draw another box. Now remember, in the first example, I made the x values the same because they were both 100. So then I created a variable and then I bound 100 to that, and then they were the same, right? Well, you know, there's a much easier way to do that in a diagram editor, right? You just have guidelines, right? There are edges here. Whenever they're about the same, the edges appear, right? So we can add the guideline here, right? And now they're always going to be the same. I would really love to have this in PowerPoint, and the PowerPoint team doesn't really listen to me, but still, this is really useful, right? I'm actually writing a program without actually having to write any code, right? So now we can turn this into an array, right? Let's turn this into an array. Here, now we're going to have an array of boxes, but nothing really happened. We just said we went from 2 boxes to an array with 2 elements, right? Again, we're kind of climbing the ladder of abstraction here. We started out with 2 things. Now we have an array of 2 things. And of course, once you have an array of 2 things, it's only a matter of time before you have an array of n things, right? Now, let's look at that constraint that we did before, which I believe is that one, right? And now there's another option here, right? Right, we don't have to just bind those 2 rectangles together. Since it's part of an array, we could bind all the rectangles together on the left. Now they're all bound. Now they're all aligned. We can also do the same thing here, right? I can add a little thing over here that says top to bottom, and then I can click on this. Now they're all bound top to bottom, but of course only those 2 are. Now if I click on this guy here, we get another option. We can say, okay, do it for all the elements, right? Now they're all aligned, right? And if I add more here, it'll just continue on. All right, so let's get rid of that. We could also do things like I can draw a large rectangle here, and I could draw 2 rectangles inside here, inside the big rectangle, right? And now I can take this guy here and I can bind it to the edge. Right now when I move this rectangle around, it'll always be there. If I move this guy, it'll move the rectangle, and if I move this guy here, it'll just be free flowing, right? But let's look at that constraint. Click on it, right? There's another there's a more general interpretation of this constraint. We can abstract it further. We could say the right of the rectangle is max, right? So I can click on this, and now we've gone through, and the example looks exactly the same. When you abstract your program, you don't change your example, right? You just change the constraints of your example. Then the future modifications depend on the abstract behavior, the new abstract behavior that you've just specified. So now there it is. As soon as this guy is this guy has the edge further, right? The box expands, and we can also do the same with this side here, minimum. Right, now, there we go. Don't say you crashed. All right, there we go. Right, so we've this is a bit more complicated behavior than you get in just aligning the edges. Let's make that go away again. Now I want to bring back this guy here. So this is a string, right? So this is another Lexing example. Right, if I edit this thing here, right, you can see the one down there changes, right? So I'm going to draw a rectangle, and I'm going to draw another rectangle inside this one. Now that really should have been inside. Let's get rid of that guy. Just turn it off. All right, let me try this again. Hopefully I'm not too nervous that I can draw within the box. Right, now we have this guy here, and I'm going to click on this one, and it has data, right? We can actually go ahead and bind this data to this guy up here, right? Now, it's just a bunch of boxes with nothing in them, but it's the same number of boxes in the one down here. So we can click on this guy and say, I want to look at the kind. So we have text, which is being shown down here, but we can also show kind, which is a Lex token that's been pre-computed for this example. And we can see it's ID, white space, ID, white space, ID, new line. Right? Now, I can add a point on this uh, box, right? And we can align it to one of the edges here. So I'm going to align it here, right? So now this is aligned to the the right hand edge of the fifth token, I think, right? 1, 2, 3, 4, 5. Yep, right. But we can also click on that and we can change that to be ID or white space star, right? Which is also 5 tokens at this point. But then when I go ahead and modify this, right? Well, that's not right. Second space. You can see it's changing. All right. So what I can do is I can take those tokens here that I'm parsing, and I can then bind that to another rectangle here and show the text, right? Something's wrong. There we go. All right. So you can see we get the first line of text here in the box, right? Now we can add a second point here after the new line, right? Bind that to the edge, make it relative to the first point, and now see what we have here. We have, oh, we could parse a clean star of new lines, or we could just parse one new line. And actually here we just want one new line, right? And then um, we can do a second one down here, but we're just going to clone this guy here. Takes a while. It's a little bit slow. Now, I just cloned this rectangle down here to this rectangle, but this guy doesn't, it only clones the internal connections. It doesn't clone the external connections. So it didn't actually get this binding here. But that's okay because we want to bind that to the rest of this over here. Right? And now we see we have C and D, and that happens to be the line 2. Right? And then we could do that in an array ad infinitum to get it, like, let's say, a text editor that works on tokens. Okay. So then we could, edit this a bit. Seems to work better when I add things to it. So let's just do it that way. F. Not the fastest thing in the world, but get the point. Okay? So we did this without writing. Well, we wrote code, obviously. We did abstraction, but it's in a way that's a bit different from the way you would attack it in a textual language. Okay, so let's go back to the slides. Where is my thing? Okay, so what I just showed you was my attempt, my early attempt of sort of resetting my research and trying to attack the core of the problem, which is, we don't want to just provide this feedback loop that looks cool. We want to actually make programmers more productive, and the way we can do that is to augment their thinking. Okay? But there's a lot of challenges here, right? How do we project non-visual logic into 2D, 3D spaces, right? We're able to do it sometimes, like with lexers, because you can just think of them as boxes, right? I really believe, and this is not true for everybody, that whenever we think about problems, when a lot of us think about problems, because I don't want to generalize here too much, we actually convert them into to graphical images, and we work on them in our heads that way. Or if we're using the notepad, the paper, the boxes, and the circles, we actually go ahead and we already do this for ourselves. It's very custom, and it might be challenging to capture that in the computer, right? We lose the zen of text. Right now, the program just isn't there in front of us with no distraction. Right now, we have this visual interface where we have to uncover the logic. Can we define this as a general language? That's an open question. And visual design language is actually much harder. This UI sucks. And hopefully, as we get more experience, it will suck less. But the main challenge here is how do we augment our minds without limiting it, right? Because if you do a half-assed job on this, right? I mean, it's just going to make you slower because your mind is actually really efficient, right? So we have to do a really good job here, right? So I'm going to put out a call to action here. It's like I want you guys to think about where your programs come from and how you could actually have the computer help you out in coming up with your programs, right? And send the ideas to me and I'll copy them and who knows, or maybe build the next great programming system. Okay. There's a lot of related work in this space. I mean, a lot of it's from the 90s. Some of it's from the 1960s, right? So I mean, always building on the shoulders of giants, right? But I'm not going to go over that. So, how much time do I have left? 4 minutes. Oh, wonderful. Great. I'm at the end. Okay. So, in the conclusion, right, today we are dealing in the age of super programmers, right? Really good archers. If you guys seen the Avengers movie, that cockeye guy, he can like hit anything on the first try with just shoot the arrow, right? And it's kind of like using the force, right? Because we expect our programmers to be really super good and like, doing everything in their head, and they just use the force and they're done with it. They destroy the Death Star. Okay? Well, there's another vision coming out of programming that's probably worse. The AI programmers, if in Avengers, right, Ultron was the enemy, right? This guy is going to do everything, and he does it really well, right? Of course, hopefully we're like 100 years away from that. Once we get there, programming is over, but I'll be dead, hopefully, right? And of course, that doesn't have a lot of positive implications for society. Here it is. This is where I think the next step is for us, right? Is the Iron Man programmer, right? Instead of having machines do the work, instead of having people being really good at doing the work, let the computers do what they do well, and let us do what we do well, right? With an augmented programming experience, right? And it's really cool because in these movies, right, programming is really something that you can't make look fun in the movie. So they wind up doing these holographic interfaces with lots of interaction going on. And yes, it's fictional, it's fantasy, but I think it has an element of truth there. Right? And of course, this isn't using the force, this is just we have better targeting computers. And that's it. I'm done. Do you want to ask a question? Okay. In the back corner.
Thank you. Most of this work seems to be focused on how to write programs. How about reading programs? Because most of my work is actually reading what I wrote yesterday. So.
Right. So I haven't done much work on that yet, but I have thoughts. I think if you have a concrete example to sort of that you use to build up your work, then you go back to that concrete example when you want to understand what you did. That can be very empowering, right? It's just that right now I look at the code and I'm reliant on the comments to tell me what was in your head when you were writing that code, or when I was writing that code even, right? But with the concrete example and maybe getting more of that thinking out onto the computer, we can solve that problem too, because now you have the concrete example that you were working with, and you can actually see the code work. And maybe you have a few concrete examples that you use to develop the code. But each of those concrete examples is very important in understanding the code. And I hope, and I have no evidence, that this is where that goes. Shriram?
So thanks for the talk. 3 questions. So, it's clear that this is a great vision for talking about how to, say, build up domain-specific programs, right? Like, I would never want to write a regular expression again if I could have one of your tools.
Thanks.
Right? So generating a regex this way seems like the obvious way to go. So one is, so the concrete questions are, one is, you gave us this, you early on put up this picture of, look, here's this horrible mess. This is what happened when people tried to do visual programming in the past. I was hoping to hear an answer to how it's going to be different this time. Right. So the second one, right. So the second one is about data drivenness, because I don't see enough use of using data to drive the design of the program. And the third question is about, there's great tools here for helping people discover existing abstractions, like in your text editor where you showed us, here, you can have this function, or you can have this other function for writing a lexer. I worry that at that point, people are going to become more dependent on using existing abstractions, which is great. It's hard to find them right now. and not enough emphasis on building their own, so they don't actually grow a toolkit as a programmer.
Right. So the first on the first for the first question about the visual languages, this is showing non-abstract visual programming or progressively abstract visual programming, which I don't think there's a lot of work there, and I think that kind of makes it better. And the reason why we go visual programming is not because we care about syntax errors, which is what the traditional argument is, but it's because, we get that 2D space to work with, a lot more canvas, a lot more things to click on, basically. And the second question about data driven is I get to that sort of at the end, right? It's more of a work in progress where I'm actually binding these boxes to that data in that example. But yeah, it's definitely something that requires a bit more work. For the last question, I think, so definitely there's a lot of the system has to support the creation of new abstractions via cloning and that kind of thing. First of all, you have to have the ability to do new abstractions, right? Not just use existing ones. As for where you use an existing abstraction, where you do your own, I hope that becomes like evident. Maybe you can start from an existing abstraction and realize that it doesn't work out and abstract your way away from that into a new one. But that's the best story I have for that right now. Okay. Yeah, yeah. Felicen?
Thanks. At the very beginning, you said you wanted continuity in programming. You need this continuous curve, and because of high school, continuity is often distorted into this smooth curves that we draw on a piece of paper, but there's a lot more to continuity than that. Do you think that your visual programming is a programming method for small changes to the problem statement, resulting small changes to the program?
I don't think that's possible.
Yes, it is.
Okay. I guess it depends on how you define problem, but I mean, I've kind of given up on the. I
I
mean,
give you an example that based on a tree run. Suppose you have a data organization
uh huh.
and you program with this, and then you add a variant of data. Like you have some kind of telephone, you have a terabyte of telephone records, and now you get a new kind of telephone record, like because we invented cell phones or whatever.
Right.
And there's a very small change. It's one extra kind of record over the 15 that we had before.
Right.
How would this be reflected in this program? Would it be a small change?
I would hope so, but I haven't handled that
I
case
think
yet.
that's since you started from that point, it would be an interesting point to explore research-wise whether small changes in the problem, the beginning of the program,
Right.
really small changes. So our method, the one that you and I developed, clearly go there, right?
Okay.
But I think it could be transported at least for some domains into
Right.
your
Right.
world, and that
Right.
would be really cool
Uh,
to confirm.
so let me qualify my statement. I have given up on continuity in general, right? Or continuous in general, right? There's a lot of things that go on in programming that's like step. So you have to.
You picked the wrong topology. Come on.
Right. But anyways, you have we have to redefine what it means to be continuous, to be fluid, right? It can't just be the changing the numbers around, right? So there's a lot of, it could just be progressive abstraction, for example. And in this case, sounds a little bit like progressive modification or something. But yeah, it's something I need to think about more. Uh, this one over here.
Hey, so at first you showed us something with drawing boxes and circles, and I've seen a lot of drawing boxes in live programming, and I was going to ask the question, wait, but I'm not drawing boxes, I'm a compiler writer. I want to see how I can do that for writing compilers. And then you showed me this example with the Lexer, and I was like, no way. But this triggers another question. But the thing is, the Lexer example looked very different than the boxes example, and it kind of triggers the question to me that it seems like we need to reinvent live programming for every single domain, and it might not scale to general purpose programming in a sense.
Right.
Could you comment on that?
Yeah, that's definitely true in the sense that each domain has to kind of come up with this new visual language, and hopefully it's something that you can build within the system itself, right? But that's something you have to invest in. So it could be that we're talking about, domain-specific languages is a big thing now, right? Maybe we're thinking about domain-specific thinking environments or domain-specific, you know, visual modification environments. Hopefully we can make that easy. I don't think there's a one true visual language to rule them all, right? Which is kind of where I was getting at in the generalization comment that I made about the challenges of this technique. We have.
Hello. I am a hub-based signal scientist. That's a lot, but uh, I am trying to analyze EEG signals, and I would like to see a lot more of live programming within data science and scientific programming. Because right now, what I use is Jupyter, is IPython notebook, and it's kind of strange to just switch between visualizing signal in my head
Mm-hmm.
and visualizing how I have to translate to NumPy and SumPy and SciPy to actually do something with it. And for example, Wolfram language tried to do something with that, tried to do some real-time visualizations with just sliders instead of trying to rewrite a data structure in NumPy. Uh, don't you think that we can approach live programming for scientists at first and basically learn at first from, for example, signal analysis, and then try to take that to software development or general programming?
It's it's definitely valid, and there's people working on that. I think if is Luke in the room? Okay, yeah, you should talk to Luke back there. He presented a paper at the workshop a couple of days ago in that area. Um, yeah, some of us are actually going in that direction. I'm not really well versed in data science, visualization, and signal processing. Um, so maybe personally, I'm just kind of knowledge deficient in that area. But yeah, it does sound like a good area that's ripe for it. And I think I have had conversations with Leo Majevic about this too, where he says that this is a good place for this kind of work.
The state of the art right now in industries to get this feedback loop is usually unit testing and generative testing in order to specify these constraints. And there's a huge gap from what industry is doing right now and this visual approach. What are your thoughts on a step forward from evolving what industry is doing right now towards this?
Oh, I don't think there's a small step. I mean, there's definitely a lot of people working on sort of the live feedback and the program running while you're editing it and adding a few features on top of that. And I think that will kind of whet the appetite, but I don't think it really solves the big problem, right? Which is sort of how do we get in your head, right? Because all this stuff kind of exists on the outside, right? And the unit testing and the continuous unit testing is all sort of post facto, make sure I don't break anything, but it doesn't really help you. It helps you figure out when you've done something bad, but it doesn't really help you figure out what the good thing is, right? So it's a bit of a big leap, and I have no good answer for you.
In your examples, you seem to equate live programming with visual programming. Have you done any research with like oral feedback or smelly code smells, or is it because we use in our live environment when we're actually interacting with the real world, we obviously depend on a lot of different senses.
I think the eye is actually the highest bandwidth per to your head, right? So I think it makes sense to look at either 2D or even 3D graphics in the future. Then everything else is sort of like low bandwidth. That's my best answer.
Cool. Thanks.
Okay, good morning. I'm going to talk about the future of programming will be live. So in the beginning, we have computers, we have binaries, electrons flying around, not very useful for getting work done. So we applied our, good friend abstraction to make the concrete bits into more abstract symbols that we can then manipulate and, write our programs. Right. So and then, this evolves into programming languages. Very useful. Programming languages help us, they give us a language for our abstractions. They allow us to, you know, you know, record our abstract thinking and provide a limitation of that thinking and help us write programs. But where does the computer actually fall into the process of programming? So, we think really hard about our programs. The languages guide our thinking, but the computer is just kind of sitting around there doing nothing. It's not actually helping us think about our programs. My taskbar is completely missing. That's not what I wanted. All right. So here we're going to have a textual environment. This is a little program. Can you guys see that question mark okay? I hope so. The color is not very good on this projector. Right, so I type a question here, and it's basically a placeholder for a statement. I call it a holy term, right? It's like, it's a hole in your program, and then you can shape it into something else. So we can now do co-completion on that, and we can draw a circle or draw a square, right? And what happens is that we get a little draw command here, and these holy terms are substituted with, actual values in your program. So this is a geometry. There's even a color here, which is that color you see down there. And of course, the nice thing about this sort of holy term style of programming is that, you every time you add something to your program, you have something that's executable, right? Even with default random values, but at least there's something there so you get your feedback right away. So let's change that into a circle, right? So we did co-completion again. And then we get other arguments here. This is a position, right? And the color's there. So let's easy. There's an Olympic sport for archery, and there doesn't need to be one for water hosing because water hosing is very easy. And this really is all about feedback loops, making the feedback more continuous, more integrated, more interactive, right? And, the better feedback loops we can get while programming, the better programs. The faster we can write programs, the better programs we can write. So I've been working in this field of live programming since 2007, and I did this this little language where you could type your code and you could see the output of your code while you were typing it. And I thought it was really cool at the time, but in retrospect, it wasn't that great because, as Brett Victor says, you can see sort of the typing, you can see the output, but you can make no connection between the two. So live programming has to be more than just running your program or editing your program while it's running. And I tried some other things, which I will talk about in just a second in a demo. But I think the overall experiences here, I try and keep failing, but hopefully we can do better. So let's get going with the first example, the first demos. And where is it? Oh, it's not helping us write our programs. It's just sitting there and waiting for us to know what our programs are before we can type them in. Well, this isn't entirely true, of course. We have static type systems that give us errors that allow us to, tell us when our programs are bogus, or co-completion that allows us to sort of figure out what to type next, or even IDs that have debuggers. But I feel like we should be able to do more with that. And so live programming is this idea that today programming is like archery. We think about our programs and we type them into the computer, and if it's wrong, then we go back, rethink, retype, and start the process over and over again. And then if you have a REPL, you can make that a little bit faster. But then if you have a large program, some programs don't work really well in REPLs, and it's just kind of like it's nice if you can have a little bit of a feedback loop while you're programming, but a lot of times you don't, right? And live programming, in contrast to archery, is like using a water hose to write your program, right? Water hose, you just sort of aim the water hose and you hit the target, bam. It's really add a position in here. It keeps jumping around, but that's just the way the random values work, right? So now we have a position with a tuple. We can do 100 by 100, right? Or I might want to do 200, right? But every time I edit this, right, you can see it's all jumping around and everything. So let's do this smoothly, right? We can just scrub to 200 if we want. This is called scrubbing, by the way. I'm using Brett Victor's terminology. It's basically the idea that you can have a value in a continuous domain and smoothly adjust it, right? And we can scrub this one too. We can also scrub both of them, right? But actually, that's kind of stupid. Let's just move it directly, right? I mean, that's really what you want to do. Right? We can go to the color and we can change it to blue, but we can also scrub the color, right? So you just go around and choose a new color. It could be lime, or we can change this to a tuple, right? And we can do a little color picker here, right? So let's